All right, thanks for coming, guys. Thanks for your time. Before we get started, just some kind of room rules, I guess, or room info. If you look at the top of the slide here, we're trying something new. Basically, you can open that link with your phone, and it'll bring up a Q&A section where you can use your own name or do anonymous Q&A. And we've got, basically on this laptop, a display that'll show us all your questions. So if you don't want to interrupt, but you want to ask a question, go ahead and that link's going to be shown at the top of the slide the whole session. So you won't lose it now, but put it in your browser, open it up. You can ask your questions as we go. As well as raise your hand at any point. We have a mic right in the middle where you guys can stand up and ask questions. And yeah, with that, let's get into the flow. So today, we're going to be talking about far edge and VMs and containers at the edge, as well as a nice little 5G twist at the beginning here. In terms of introductions, actually, should we go over a disclaimer?
No.
Yeah, okay.
Yeah, good.
So we have two speakers today. Myself, solution architect. I cover network equipment providers in EMEA. I'm originally from Boston. I've got about 15 years in the telco space, and yeah, I just turned 40.
Yeah, so my name is Timo Jokiaho. I'm known as a simple Finnish engineer at Red Hat, which is all true. And I started to use hexadecimal numbers to express my age, so I'm 40 as well.
You're 40 as well?
It looks better. It looks better.
You could be a brother from another mother, you know?
I could.
We got red shoes, right?
Yeah.
Yeah.
Yeah, so that's who we are.
And Timo's worked in telco for 40 years, so he's literally worked in telco as long as I've been alive, so.
Yeah.
But still 40, right?
Yeah.
Yeah. So we're going to go into edge today. Before we get started, how many of you guys are actually doing edge right now? Okay, how many of you guys are doing edge in production, where you're running money-generating workloads? Okay, we got 2. Good. With that, so I guess the interesting thing that's going to be here is an edge. We're going to, did you guys see the lightning talk we had on edge on Monday? Anyone? Okay, good. So this is an expansion on what we did there. Timo's going to start off today, so he'll walk you guys through the whole, basically, RAN at the edge. And then we'll cut off the second part, which will be the use case of how you actually deploy it with infrastructure. So with that, Timo?
Thank you, thank you. I have a little bit sore throat, so I hope I can make it. I can make it. So I'm gonna walk through the evolution of radio access network in the beginning, which is one of the very, very concrete edge workloads or edge use case. So we have heard a lot about edge this week, so nothing new here. People have different definitions on what edge is. But again, I'm going to use RAN evolution, radio access network evolution, as a really concrete workload for the edge. So I start with this. So this is a eNode B evolution, which means LTE or 4G base station evolution. And on the left-hand side, that's the current model, how eNode Bs are deployed on the antenna side or cell side. So there is actually a lot of stuff in addition to the radio heads and antennas and all these things. And these 2 things which are with the red circles, it's a kind of a not really high-end computing system, but it's more high-end computing system as was planned in the beginning of 4G standardization. So there are kind of a high-end CPUs and a lot of memory, and the reason for that is that the base stations or eNode Bs, they talk to each other directly using this X2 protocol, which is a protocol which manages handovers when the mobile devices move from a base station to another. So they talk directly to each other. And also the X2 protocol is used for managing the radio interference between the adjacent cells. So it's a complex process. It's a really complex process or processes, a lot of mathematics, which have led into a complex device at the bottom of the tower, the BBU. There's a lot of stuff here. And the eNode Bs are way more expensive as planned in the beginning of the standardization because of the complexity. They eat a lot of power. They consume a lot of power. So CapEx and OpEx is way higher than planned. So all these and many others, they have these things they have led into this thinking of VRAN, virtual RAN, meaning that take as much as possible from the current eNode B cell site to the edge data center, which is on the right-hand side. So that's why the virtual BBU, baseband unit, is a first real concrete edge workload. And it doesn't really make sense to build an edge data center only for BBUs. So operators will deploy any other use cases on that same edge as BBU, which is excellent. So what happens when we do this, and this is happening as we speak, many, many places in the world. So again, the cell sites will become way simpler, cheaper, less power consumption, and all these nice things. That's all cool. And there is still the X2 protocol, of course, has to be happening, but it happens between the virtual BBU instances on the edge data center, not between the antenna sites. A big difference. So that's all cool. And obviously that edge data center, it is a target or candidate for to deploy with NFV architecture if people choose to do that. Some do. It can be something else as well. But I'll show you why it is a good idea to use a consistent architecture starting on this edge data center. So this is 4G. Now let's look at the standard. This is ITU-T standard, but it's compliant to 3GPP and whatever we might have. So the far left is the same as I had on the previous slide. The 4G eNode B virtualization, the same thing, virtual BBU managing several antenna sites, all good. And the other one is 5G, where the standardization is going even further. So they even divide the 4G BBU site into two separate entities called DU and CU. Not very much imagination, but it's a distributed unit and centralized unit. And then, of course, the same protocol, it's called XN because there will be some changes on that protocol on the CU side. And again, the antenna side is as simple as ever can be. And why is it's divided into two? Why do we have DU and CU? The reason is that with this model, operators can deploy the 5G new radio in very, very many different ways. So they can keep antenna site simple and not co-locate DU in the antenna site and not co-locate the CU in the antenna site. That's all good. But in many cases, if there is no fiber, for example, to the antenna site, you have to co-locate the DU into the antenna site because there is still a lot of microwave-based connectivity for base stations, and that's not good enough for this purpose. So it has to be fiber, then you can take DU away from the antenna side. And it also depends, the deployment models depends on whether you are deploying on the densely populated downtown area or rural. And that's why standardization did a good thing, just to have these. Give flexibility to the operators to do that. Now, the blue thing is, it's called functional split models. So there is a radio stack in the base stations, eNode Bs and GNode Bs for 5G, and there are different split models. And if you go to the right-hand side where the radio is, and you make the split as close to the radio as possible, that's called low-level split. And when you do the low-level split, then the requirement, latency and bandwidth requirement between the antenna site and the DU is really, really hard and difficult. Doable, but hard and difficult. When you do the split, like option 2, 3GPP specified, that's called high-level split. and then everything is kind of easy. So there are many different reasons why people want to go towards the radio interface for the split models. The current splits which are happening, they are not these low-level splits yet, but that's where people want to go, or these service providers want to go. And just a very high-level characterization of the platform, whether it's a virtualization platform or container platform for DU and CU. So CU is again, edge cloud or edge data center, highly distributed, many instances in the network, but it has still requirements against, let's say, OpenStack, for example. Has to be lower footprint, has to be many of these things, but nothing really dramatic or very hard to do, so all good. So the DU platform, on the other hand, is a real-time platform. So you need to have a real-time execution environment for your VNFs or container or applications in containers, whichever you have. You need to have a precision time protocol between DU and the remote radio to have a sub-microsecond accuracy on timing between DU and radio, because the 5G radio is completely different than we have ever seen. It's based on kind of utilizing the interference and forming beams from the antenna to the individual mobile devices, which is a very, very different model. But it's a really timing sensitive. But this is under development as well, as I will show you soon. Now, this is a kind of overview of the whole thing. So the upper part is the current LTE, so everything is on the cell side. That's the normal eNode P deployment. Then this next one is having only radios, remote radios on the cell side and BBU on the edge. And then even LTE will adopt 5G model, DU, CU model. And the radio can still be LTE or will be LTE. And then we go to 5G. And this is how the edge then, from at least my point of view, looks like. Again, there will be other workloads on this edge. And again, BBU and CU will be the first edge workloads and use cases. And it's a massive scalability and distribution deployment. If you think about, I'll give you a number, which is not really 5G number yet, but let's take China. They have 3 mobile operators: China Mobile, China Unicom, and China Telecom. And collectively, without 5G, they have 6 million base station antenna sites in the big country. 6 million. And when they go to 5G, the ranges of the base station is going to be a lot smaller because the frequencies go to the millimeter wave. So it will be at least tenfold, 60 million, or maybe not that much, but it will be tens of millions of base stations. And that really makes sense to make an antenna site as simple, cheap as possible. But from the software point of view, it's a massive scalability and distribution challenge where the automation, orchestration, all these things will play a crucial role. Now, a real-life example is, there was a Cisco presentation this week on Rakuten. Rakuten is a service provider in Japan. They have been like an Amazon of Japan for ages, and then they have been renting capacity, cell network capacity from KDDI, Docomo, and SoftBank. And then a couple of years ago, 1.5 years ago, they got this great idea that, hey, let's build our own physical network. And this is the only greenfield mobile network built in the whole world, the only one. And they started completely from NFV-SDN principles with no legacy at all anywhere, which is good. Now, when you look at what happens there, there's a remote radio head. So this is a 4G radio because there is not much 5G devices yet. So 4G radios, but the network is 5G according to 5G standard. And there are a lot of partners in this game. So the remote radios are coming from Nokia. So Nokia builds the antenna sites and provides remote radios, but nothing else. So there is this industry standard interface called CPRI from the remote radio to the DU device running on COTS hardware from Quanta, on NFVI, Red Hat OpenStack platform, and the Altiostar DU is talking to the Nokia remote radio heads. And then the same thing going towards right, another Quanta server cluster, whatever you call it, running Red Hat OpenStack platform as a NFVI, and CU functionality from Altiostar again, the startup in Massachusetts, great company. And then Rakuten is planning to start deploying other edge applications on the CU edge compute. I don't know what those even are, but that's what they will do. And then when we go towards the core network, the same thing again, Quanta COTS hardware, NFVI by Red Hat OpenStack, and the Evolved packet core from Cisco, IMS from Nokia, and GI LAN from somebody, I don't know who. So a big multi-vendor case. And this goes live this October in Tokyo and Osaka only, but in Tokyo and Osaka. And by 2025, Japanese government has told Rakuten that they have to have full coverage in Japan. Not much time, but they do have this advantage on playing on the green field, no legacy, no nothing. So Rakuten has a possibility to move workloads across the network depending on the application needs, because there's the same platform all over the places. Very important thing. So this is a high-level diagram just showing kind of the same thing and having the network slicing dimension from 5G spec. So 3 slices, the ultra-reliable low-latency communication, 1, and then enhanced mobile broadband, which is a kind of a default use case for 5G, and then machine-to-machine communication, IoT. And the idea of this thing is that when you have the same platform all over the places, you can move your user-plane functionality, the black boxes, UBF, user-plane functionality, you can move them closer to the edge, like in this ultra-reliable thing, the first slice. You can move it as close to the edge as possible. And then enhanced mobile broadband, it doesn't matter that much, so it can be closer to the core network. And IoT, it really doesn't matter where UBF is. But the system provides functionality to, or possibility to move these functionalities or workloads anywhere. Taken into account that the fundamental number is that the packet over the fiber can travel 200 kilometers in 1 millisecond. That's not quite speed of light, but speed of light is in vacuum, but on fiber it's 200 kilometers in 1 millisecond. And if you take that into account, you can kind of flexibly move functionalities into different places. So this is kind of concludes my part. So I talked about the RAN and mobile network, because that's what I've been doing for 40 years. So I'm by the way, the 1G master. That's what I'm also called. People talk about 5G, but I talk about 1G. So I talk about that, and the same model, edge model, applies to Metro Ethernet. It applies to fixed access, GPON, ONT, OLT, and all the others. So there's always the edge component in all of these places. Now I'm going to hand over to Eric.
Great. Thank you, Timo. So it looks like, let's see, one question we had, Timo, here is, beside performance aspects, is there a significant cost savings implementing edge infrastructure? I guess this would be in the 5G case.
Significant?
is there significant cost savings implementing edge infrastructure in the 5G case?
I don't think there is if you only utilize the edge for the managing the radio access network. But when you start applying any other edge use cases, like any of these, for example, on the same edge data center, then the cost savings start really kicking in.
Great, thanks, Timo. So before I get started, I wanted to ask, do we still have the people in the room that had edge use case in production in the corner? I think they stepped out. Okay. So what we'll cover now is an agnostic view of what edge is going to be in a little bit more detail than we had at the lightning talk. What we're going to cover now is basically 3 levels, which you could do level 1 now, level 2 a little bit later, and level 3 in the future. We'll cover product agnostic views. So I'll be talking about Kubernetes and about OpenStack. So I won't be talking about OpenStack from Red Hat or OpenShift from Red Hat, but it could be correlated. Just to be clear, we're talking communities here. So with the things you see here, we had a lightning talk yesterday that was kind of cool that looks just like the top left box. Did you guys catch the lady that was talking about the edge use case with the welding arms? So that was one here that we had. The one that Timo covered is pretty much 5G, so you got a good view. Even if you're not in the telco space, you now know what a CU and DU is. It's a G node B, and how they're separated functionality-wise across the edges and in the core. What we'll get into now is the kind of edge use case mapping. So we have here basically the edge scenario with the top and the bottom, correlating back to what Timo was talking about. The way to look at this here is if you look on the far right, that would be your core data center. Then you're going to have a mobile backhaul that'll go to your edge site. And this edge site would have, in this case, OpenStack controllers and OpenStack compute nodes. And in there, you'd be running maybe some services like, what do you think? Would it be the DU or the CU? How many think it would be the CU running in the edge site? Okay, how many think it would be the CU? Or the DU? How many don't think anything is running there? How many are too tired late in the day to put their arm in the air? Yeah. Okay, so the way to think of this, there's 2 edge sites here. It's kind of tricky, right? You have an edge site on the far right. You have an edge site in the middle. And then you have a core on the far right, right? With your central unit and your distributed unit, your CU is going to be running at that larger edge, right? And then basically on the very, very close part to the radio is where your DU is going to be running, right? It's showing up there on the diagram as DU. The piece to take into account here, let's forget about 5G. Let's think of, I was going to try and figure out what use cases they had there, but let's assume we have a use case of Netflix video CDN or delivery, right? You want to be able to watch your Netflix. You don't want to have to wait for it to load. Maybe you want it loaded out at the cell site if you're Netflix, so that basically they can get 4K video and not have to wait for it to cache. In that case, you would basically cache it in both edges, but there wouldn't be a difference between what the functionality was. You have a cache maybe with all the movies at the edge, and a cache with what you see those users using at the far edge. But the case here is that those edge nodes are a little bit different. If you were at the lightning talk, we talked about distributed compute node. And there was a couple talks this week about using compute nodes on a separate layer 3 network than your typical OpenStack. What that means is that you install OpenStack in that edge site with the controllers and computes. And then you install distributed compute nodes out at those far edge. So we're talking edge in the middle, far edge on the far left here. With that model, you're having an OpenStack infrastructure, you're having OpenStack controllers at the edge, and OpenStack computes at the edge and the far edge. And then you're putting your workloads in both of those places. Now, the thing here is that in order for that to work, the computes have to be less than 100 milliseconds away from the edge. So the far edge has to be able to have a latency of less than 100 milliseconds to get to the edge in the center because of stuff like RabbitMQ and messaging timeouts. So that's kind of the rule of thumb here. If you're using OpenStack, build your edge, put your controllers out there, put your computes out there, and then when you build your far edge, put your computes out there that make sure you can get less than 100 millisecond round trip time so that you don't have issues with the actual infrastructure communicating with each other. Any questions before we go over to the Kubernetes container one, which I think is the, yes? Mm-hmm. Mm-hmm. Yes. So the question is, those are computes out there. If there's a failure, how do they recover? Okay. So the way to look at this, the caveat I'm not covering, there's a lot of caveats, right? So one thing to think about is your storage is going to be ephemeral in most cases. There's not a good solution today on how you'd run Ceph. Do you really want to run 15 gigabytes of data across your WAN link to the far edge every time you bring up a VM, or even caching it there? Or let's say, let's not get too deep in the storage part, but right now the storage is going to be local and ephemeral on the far edge use cases. And the question being, what happens if you lose your WAN link or it goes down? So today what would happen is you wouldn't be able, of course, deploy anything there. The VMs would continue to run, and then when the compute node comes back up, you need to have a recovery mechanism for the compute to show as active in the controllers in the edge site. The other thing to keep in mind is if those nodes are powered off, you probably are in a better case of just trashing what you have in that standalone node and redeploying that specific compute node via either whatever install mechanism you have. In Red Hat, it just happens to be Ansible-based or OO. So you basically do a Pixie boot and the network connecting. So let's say you have 10 routers between your edge and your far edge. Each of those would have to have an IP helper command in there to allow the DHCP request to come from the far edge all the way to the edge, and then the reply back with the TFTP server and the Pixie boot server address and all the stuff that the node needs to do Pixie booting. But again, let's not go that level. But if you guys want to talk about that afterwards for OpenStack, hit up Timo and I. We got business cards. We can make links, and we can even talk agnostic about just OpenStack in general. Good. Thank you. Again, you can ask questions too anonymously up on the link up there. Just open it with your phone and you can put stuff in. Now, Kubernetes. Who here has, we don't have many people doing Edge, but how many people here are using Kubernetes in their lab or have actually tried it out? Okay, good. So I see about 50%, maybe 60%. The model is going to be the same here. You have Edge and far Edge still, and you've got the same concept in OpenStack you have in Kubernetes. You have these master nodes that are acting like controllers. You have other things like infrastructure nodes, which are basically like your VTEP gateway, where you're basically going to be terminating your network traffic and having kind of your ingress egress for network flows. That would be on your edge site. Now on your far edge site, in this model here, we're looking at having just the worker node. So in Red Hat, we call it node, but some other people would call it here a worker node or whatever you want to call it. But it's the Linux server that has runc on it. It has kubelet, it has kubeproxy, all the stuff that you need to run the container. This model, I think, is a really good one that you could do today, right? So if you have less than like 10,000 nodes in your use case, maybe you want to do something like this that can actually scale. Now, granted, you probably have to do a lot of stuff to do 10,000 nodes. You can't use a /24 subnet for your node IP addressing, of course. There's not enough IPs to fit 10,000 nodes. But of course, looking at it, you could do this quite easily today with what's in the market. If you remember, what is it, Rakuten, Timo? If you looked at that, it was IPv6 networking. There is no end-to-end IPv6 networking in Kubernetes yet. So there is a ton of features missing, especially if you're looking at the telco. If you need SRV, DPDK, if you need multiple NICs on the container, you got to use something like Multis or Danem from Nokia. They all have different types of multi-NIC features today, but it doesn't work in Kubernetes natively in the sense that if you're in Kubernetes, you'll see all those NICs showing up. So if you have a use case and you need those features, you should reach out to the people who are developing. So Google's developing Kubernetes, Red Hat is probably number 2 in Kubernetes. Look in the Stack Analytics, look who's developing that, and work with those partners who are working in Kubernetes to develop the features you need. So as of today, multi-NICs missing, SROV, DPDK, the user space. So if you guys use DPDK in OpenStack today, and you're getting high performance, and you're dedicating cores, if you saw Frank Bowden's session yesterday, he had a really cool session of where he showed basically doing CPU pinning, aligning all the resources so that you got deterministic behavior and no packet drop. Excuse me. that stuff isn't there yet. So if you look at this and you try and deploy it today, you're going to just get an IT workload type of an environment. You won't get a high performant environment. Those things are being worked on, but they're coming slowly. We have in the late release coming out, I think, in a week. So next week, there's a summit in Boston where, for example, Red Hat's putting out our next major release of OpenShift, which is our Kubernetes container distribution. In there, you have things like CPU pinning. You have SRV. You have Multis for multi-NIC. But again, some of that is GA, some of it's tech preview in there, and you'd have to figure out what your workloads need. Now, going back to what we have here, your distributed unit is just a node running containers. There's no control out there. It's just an isolated node running workloads. All your master nodes and controllers are sitting in the edge. Now, what happens if you want to have completely isolated DUs? If you want to, or let's say far edge nodes. If you want all of those to be isolated, right? So let's say your WAN link goes down, but you want that entire Kubernetes deployment to function, and maybe the people out at that site to be able to manage it. That's a little bit of a different scenario that wouldn't work here. So the third scenario, and this is the one where during the lightning talk, we're talking about something called Cloud API. And I think if you guys were in the keynote, you heard some people talking about Metal Cube with Ironic and some other things, which are pretty cool. That's what we have in the other model. So before I get there quickly, who knows what kube proxy is? Okay, good. Who knows what a kubelet is? Okay. How about run C? Okay, perfect. So let's do a quick like lower level look at this. So you get your compute node. Then you have run C. Run C is going to take care of all of the stuff like setting up namespaces, isolating the container into its own kind of, let's say, box. So it doesn't affect the other containers next to it. Once you get that running, you've got something basically like Cryo, which is your Kubernetes runtime and engine. And in there, you're going to have kubelet and kube proxy. The thing to take away from this slide, which is important, is that you always have in Kubernetes a kube proxy on the first VNIC that's in containers. We're not talking about multi interfaces in the container. That kube proxy, let's say all of us in a room are a pod, but we're all the same application. We're all doing the same thing. How does a front-end website, let's say we're all a database, how does the front-end website know to reach us? Let's say one of us has has to run off and get out of the room for a second and come back and have to be reinstantiated. Probably gets a new IP address. How does that front-end website know how to reach all of us? How does it know what IP address it got? The thing that tracks that is basically kubeproxy and some other services underneath. And it basically is using a proxy service to mask all of us so that we're reachable at one IP address, but then behind there we have all of our direct reachability. So kubeproxy is important to the extent that it's the internal private IP address of the service, but in that service there's probably going to be 100 pods running. Who knows, maybe more, maybe less. So keep that in mind when you look at this. The worker node has what's on the far left, right? Or the node, which was at the far edge. And then the edge site, which we were calling, had the masters and the infrastructure, and probably nodes as well, would have the stuff on the right, like part of the scheduling and other things. Okay, we get another question here. For distributed OpenStack, you recommend a max delay of 100 milliseconds between control and compute. Any recommendations for max delay in stretched container deployments, working in far edge and control edge? Yeah, one thing I didn't mention, and I apologize, I forgot about this. There's this concept of etcd, which is a database in the master nodes, and you could have them as separate nodes as well. You cannot put those things far apart. They need to be in the same data center or within the same rack, if you can, because there can be almost no delay between those two because of the way they're synchronizing all the time. So when we talk about stretched, the thing is that you can have the worker nodes with up to, this one here you can see we're talking about 250 milliseconds. So if we're talking stretched OpenStack, let's just make this clear. OpenStack stretch for me means that your controllers are separated by a distance. For that one, I don't know the answer to, but we have some OpenStack experts in the room. So whoever asked that, if you want to talk about OpenStack, we have Mohammed and Kareem in our room who are our OpenStack experts, and they can sit down with you and talk to you about that. For the OpenShift I can speak to, that is with the etcd consideration. You want to keep it local within the same data center with as little delay as possible, but the nodes that are actually running the containers can be anywhere with up to 250 millisecond delay. If that didn't answer your question, ask again so I know. It was an anonymous one, but I hope that answered your question. Now, 250 milliseconds. That's a lot, actually, especially if you were looking at Timo's timing constraints for 5G and 4G. With this one here, if you take a look here, you see Kubernetes icons everywhere. What that's trying to show you is those are full Kubernetes deployments. Those are full container or OpenShift or whatever you want to call your Kubernetes installation. Those are full deployments. The cool thing here is that we finally have some functionality with MetalCube, like we talked about earlier, with reusing Ironic, which is basically our Pixie Boot functionality, and with the ability for bare metal install from within Kubernetes. There's another thing here that we also have called KubeVirt. So how many people have a need to run VMs even though they are going to be running Kubernetes environment in the future? Okay, we got 3. That's good. So I'll get into that in a sec. It's quite interesting. But this is the last slide, and this is the important one from my perspective that I want you guys to take away, is where this is going to lead to. So if you don't have a time constraint to get some kind of edge solution put together, this is the way I see the industry is going to be, and maybe how the greenfields are going to look. And if you actually build some lab POCs, I would say you go for this type of model. What you have here is in the CU site, you have your own Kubernetes deployment. You have your masters, your worker nodes, you can run the containers there. And we have this other thing called KubeVirt. So KubeVirt is a way of taking KVM in a virtual machine and wrapping it in a container. So it allows you to actually run a VM in a Kubernetes environment and use Kubernetes APIs to deploy it. It's quite cool. It doesn't have any telco features. So if you need stuff like what OpenStack has with GPTK and SROV and those sort of things, you're not going to get that today. But it's being worked on. Now that's cool. You have an edge site. That edge site, you can run containers, you get a full Kubernetes deployment, you're not managing 2 infrastructures like OpenStack and Kubernetes side by side. You're not doing any layering, so you're not running OpenStack and Kubernetes on top. You're running it on bare metal here. You could do those other things, but I'm talking about probably the cleanest and most efficient way of doing this. Now, you have all those just far edge sites. How do you get that Kubernetes installed out there? We've got Ironic, we've got MetalCube, we've got Cloud API coming. So with that, you could actually use, and this is the way I see things moving right now, the Kubernetes in the central site, or what we're calling edge site, can actually instantiate the bare metal install of the new Kubernetes out at that remote site. This could be an all-in-one server that has the full Kubernetes build, or it could be 3 servers at that edge site or a far edge site, and you could deploy it however you want via the bare metal installation. So if you think about it, it's like a layered Kubernetes. You have a central Kubernetes, and then in there you could manage deploying the other Kubernetes. Now, if you put the previous two slides back and this slide side by side, can anyone tell me what the main difference is?
Control at the edge.
Exactly. The controller, so if you didn't hear that, controllers at the edge, absolutely right. So what you have here is you have, let's say there's a failure somewhere. We had a question about failure earlier. If something fails in your Kubernetes environment, it doesn't take down your edge. You have cordoned off, or let's say failure zones that are on a per far edge basis. And if you look at the resource constraints, as long as you don't have a huge requirement for low utilization, let's say you're using an ARM box at the edge. So for example, like a 5G light post and you have an ARM processor in there and you don't want to use too much resources, the previous model may be a good fit. But if you don't have resource constraints, this is the way to go in my view. Here, hold on 1 second. Why there is no infra control plane at the edge site? From where is it controlled? Okay, so if I understand that question, Danny, in this slide here, where we're talking about it, you have control plane in every single one of the far edge sites. And you have control in the edge site as well. But those controls are only for the site they're at. They're not controlling anything on another site. So in this case, you see how many do we have? On the top, we have 1, 2, 3, 4, 5 far edges. That would be 5 Kubernetes installations, 1 at each edge site. And they wouldn't actually be having any control talk going on with the central site. And the central site would only be seeing that the bare metal is installed, and it would be in the scheduler seeing that it was done. but it wouldn't actually have any control over those environments. They would have their own Kubernetes API sitting out the far edge. So for example, let's say that this is deployed now, and now you're putting your workload out there. If it's a VNF, your VNF manager would talk to the Kubernetes APIs at the far edge. So you're actually completely separating all of those environments. That's, in a nutshell, the way I see the edge going. We're still, within Red Hat, we're still developing this. Next week, there'll be some announcements around some stuff called Foundation. I'll let the business units within Red Hat share that, but it is basically around this topic. And we have another colleague of mine, Frank Sidarski, who's part of the Akraino group. I'm not sure if any of you guys follow Akraino, but this is similar to what we're doing in Akraino, which is another edge industry group. So by the way, we have a new logo, don't we? Where'd that come from? Anyone get the new logo t-shirts, by the way? They all came out today. If you haven't, go to the Red Hat booth and make sure you get your free swag, because they get a whole new set of logos. So with that, I'm going to stop there. Please let us know if you have any questions for Timo and I, and thank you for your time today.